Hello everyone. Today we will learn about 4 of the gas laws that we will be working with in this class. These 4 connect pressure, temperature, and volume to each other. A reminder, the gas laws are a collection of mathematical formulas that express the relationships that exist between the 3 main macroscopic properties of a gas. These 3 properties are volume, temperature, and pressure. Volume is the amount of space that matter occupies. Temperature is a measure of the average kinetic energy, and pressure is the amount of force applied over an area. A list of appropriate units for each of these is provided. Please make note, temperature must be in Kelvin for all of the gas laws, because Kelvin is the absolute temperature unit and therefore does not have negative values, unlike Fahrenheit and Celsius. Let us look at our first gas law, Boyle's law. Boyle's law is about the relationship between pressure and volume. In Boyle's law, we are assuming that temperature will remain constant through the change to a sample. The formula for this law is that P1 times V1 equals P2 times V2. Basically, the product of the volume and the pressure before a change occurs must be the same as the product afterwards. Pressure and volume have an inverse or indirect relationship. As one gets bigger, the other must get smaller. Let's take a look at an example calculation involving Boyle's law. A 10 milliliter sample of some gas exerts a pressure of 0.995 atmospheres. If the volume of the gas is expanded to 12.5 milliliters, what will the new pressure of the gas sample be? Since we know this is a Boyle's law example, we will use the formula P1V1 equals P2V2. What are we solving for here? We have 2 volumes and 1 pressure already given, which implies we're solving for one of the pressures. So let's plug in the variables we already know. We already know that initially the pressure of the gas was 0.995 atmospheres and the volume was 10 milliliters at that point. So we will plug those in for P1 and V1. On the right-hand side, we do not know the final new pressure. We will leave it alone as a variable, P2. But we do know the volume in the new situation, 12.5 milliliters. So we'll plug that in for V2. Now we must use algebra to solve for P2. So using algebra to solve for P2, we find that P2 is equal to 0.796 atmospheres. Our second law is Charles's law, which is about the relationship between volume and temperature, assuming that pressure is constant. The formula for Charles's law is V1 over T1 equals V2 over T2. Basically, the ratio of volume to temperature present in the initial situation must be the same as the ratio afterwards. Volume and temperature have what we call a direct or linear relationship. As one gets larger, so must the other. Let us look at an example calculation involving Charles's law. A sample of oxygen gas occupies a volume of 3.45 liters at 273 Kelvin. If the sample was heated to 325 Kelvin, what will its new volume be? We know we will use Charles's law, so we'll use the formula V1 over T1 equals V2 over T2. But what are we solving for? We have 1 volume and 2 temperatures, which implies we're solving for one of the volumes. It does say what will the new volume be, so it looks like we're finding V2. So let's plug in what we already know. We already know that initially the volume was 3.45 liters, and at that volume the temperature was 273 Kelvin. So we'll plug those in on the left for V1 and V1. Then, on the right, we do not know this new volume, so we'll leave V2 alone. However, we know that the temperature is 325 Kelvin, and so we will plug that in for T2. Now we must use algebra in order to solve this. You could either do the algebra as is, or if you set this up correctly, you could cross multiply and divide. Either way is technically correct. Your answer here is that V2 is equal to 4.11 liters. Our third law is Gay-Lussac's law, which expresses the relationship between pressure and temperature, assuming that volume is constant. The formula for this is P1 over T1 equals P2 over T2. Once again, the ratio of pressure and temperature in the initial situation must equal the ratio afterwards. This formula looks very similar to Charles's law. This is because pressure and temperature also have a direct or linear relationship, just as volume and temperature did. So as one gets larger, the other must get smaller. Let's do an example calculation with Gay-Lussac's law. The pressure inside an air tank at 298 Kelvin is 7.50 atmospheres. If the tank is then cooled to 273 Kelvin, what will the new pressure be? We know we are using Gay-Lussac's formula, so P1 over T1 equals P2 over T2. But what are we solving for? We currently have two temperatures and one pressure, so it looks like we're solving for our new pressure, P2. So let's plug in what we know. We know that initially the pressure was 7.50 atmospheres and the temperature was 298 Kelvin. So let's plug those in for V1 and T1. P2 we do not know, so we'll leave in its variable form. However, we do know T2. We know in the second condition that it was cooled to 273 Kelvin, so we'll plug that in for T2. We must now use algebra to solve for P2. Once again, you can either just do the algebra as is or cross multiply and divide in order to calculate P2. We will find that P2 is equal to 6.87 atmospheres. Our fourth and final law for this video is the combined gas law, which is used to connect all three of these main macroscopic properties, pressure, volume, and temperature, at once. The only thing that is assumed to be constant here is that the number of particles or moles in the sample is constant. We are still talking about the same sample of gas with the same number of particles in order for this law to function, and also for all three of the previous laws to function. The formula for the combined gas law is P1 times V1 all over T1 equals P2 times V2 all over T2. It looks like the three previous laws were combined into one new law, hence its name. Let's do an example calculation with the combined gas law. You have a 3.50 liter sample of a gas under standard conditions, which would be 1 atmosphere and 298 Kelvin. The sample is then heated to 400 Kelvin, and its volume is allowed to expand to 4.75 liters. Determine the new pressure of the gas. We know we are using the combined gas formula, P1V1 over T1 equals P2V2 over T2. What are we solving for, and what do we already know? We already know the initial pressure and initial temperature because of the standard conditions mentioned, and we also know the initial volume. We know the final temperature and the final volume, so it looks like we're solving for P2. Let's plug in the information that we know. We know that the initial pressure was standard pressure, which is 1 atmosphere. The initial volume was 3.50 liters, and the initial temperature was standard temperature, which is 273 Kelvin. The sample is then heated to 400 Kelvin, so that will be T2, and the volume is allowed to expand to 4.75 liters, so that will be our V2. And we do not know P2 yet, so we will be solving for that. We will then use algebra to solve for P2. Use whatever algebraic techniques you find work best for you here. The correct answer is that P2 is equal to 1.08 atmospheres. We should check to make sure this answer makes sense. The volume was allowed to expand, which would suggest that pressure might have gone down. However, the temperature was also increased, which suggests that pressure went up. So having something that is pretty close to our original pressure makes a lot of sense. So we now have 4 different formulas, and the setup for these situations looks very similar. You'll notice that a lot of the wording seemed very similar for our example problems. So how do I determine which law I should use? Well, I would guess. First, you should identify what are you trying to find. If constructing a diagram is helpful to you, you should sketch something out. Identify what things you have been given and what things you do not know. By the end of this step, you should be able to determine what equation you should use. Substitute in all the variables that you know into your equation. You should find there is only one unknown remaining. If there is more than one, you will need to pick a different equation. And then, once you have done your substitution, you will solve for the correct answer. Good luck, everyone!